Okay, so first of all, I would like to thank the organizers of the WIN workshop for this kind invitation and for giving us the opportunity to present our work. So I will review on the status, results, and perspectives of the ANTARES and KM3NeT neutrino telescopes. So the motivations for doing neutrino astrophysics, are very strong. So neutrinos are not deflected by magnetic fields. They are stable. They interact very much less than gamma rays. So finding neutrinos that point back to a given source can help on studying the properties of that source. So the main drawback, of course, of neutrinos is that they interact very little with matter. So we need very large volumes, and this is where Mediterranean neutrino telescopes come into the game. So the idea is very simple, is to use a very large volume of transparent medium surveyed by photoelectrons. And the location in the northern hemisphere is also very convenient because apart from being complementary to S-Cube, we are also sensitive to sources in the southern sky. So we have access to a very interesting region of the sky with a lot of interesting activity. So water is also convenient because you have smaller scattering length of the light compared to other media, and shorter scattering length, of course, translates into better event reconstruction, so better pointing accuracy. So the detection principle is very simple. It's based on the observation of the Cherenkov light emitted by charged particles that are produced when the neutrino interacts inside or nearby the detector. So we have basically two channels. One is what we call the track-like events with a very well-defined Cherenkov cone of light. And the other one is what we call the shower-like, which has a more spherical emission of light. So by measuring the time, the position, the orientation, and the amplitude of the hits recorded by the PMTs, we can reconstruct the arrival direction and the neutrino energy. So our signal is basically upward going tracks, and our main background comes from the top, from atmospheric muons. Okay, so I will be talking about two infrastructures that are actually deployed or being deployed in the Mediterranean Sea. We have ANTARES that was completed in 2008, which is deployed in southern France, in Toulon. And then we have KM3NeT, which is the next generation neutrino telescopes, which is a distributed research infrastructure with two sites. One is very close to ANTARES, which is called ORCA, standing for Oscillation Research with Cosmic in the Abyss. And the other one is ARCA, which is in the southernmost point of Sicily, which stands for, where ARCA stands for astrophysics. So we are mainly a European collaboration, but there are also groups from other places in the world. And the main idea is that we have two detectors, two sites, but a single technology and a single collaboration. So ANTARES, well, you all know that ANTARES is made of 12 lines, about 900 photomultipliers, arranged in triplets. The instrumented volume is about 10 megatons. And of course, we have a lot of calibration systems, slow controls, and so on and so forth. So concerning KM3NeT, well, let me just underline the three main pieces of the detector. First of all, we have the domes. There is only one dome per story with 31 PMTs per dome. That allows smaller background contamination and also better angular directional information. So the detector units or strings are the elements that hold the domes. The particular geometry of the use of the detector units depends on whether we talk about ORCA or ARCA. And then we have a complex seafloor network with the junction box and all the electro-optical cables and so on. So just to give you a global idea, what we call a building block is a system made of 115 strings or DUs with 18 domes per string, 31 PMTs per dome. So The ORCA and ARCA technologies are the same. What is different is the detector layout. So it's more compact, denser for ORCA, and less compact for ARCA. Here you have the distances between the string spacing and also between the optical module spacing. So my talk will be mainly focusing in ARCA, but there's one more talk in this conference by Veronique on ORCA, and also a poster by Joao on sterile and NSI with ORCA. So I of course invite you to follow also these two contributions. So the physics program that can be covered with these three instruments is really very broad. So we can address a really large energy range. We go from MEVs to select supernova explosions, as I will tell you later, combining ORCA and ARCA data. We will, of course, study neutrino stellations in the GeV range. We will look for dark matter and exotics in the TeV range, and also neutrino astronomy up to the PeV energy range. So here you have the effective volumes for the three detectors, for the tracks and showers channels, and as a function of the energy. So to give you an idea of where we are more efficient with the three devices. Okay, so it's clear that with the detection of the first gravitational wave events, and more recently with the detection of the Texas event by IceCube, a new era in multi-messengers has begun. So the advantage of this kind of telescopes is that you are continuously monitoring almost the full sky. So they are very well suited for studying emissions from transient sources. So from Antares, we are both receiving and sending alerts for high energy events and sharing our information with other observatories. So we perform time-dependent searches. We receive notices from the gamma ray coordinated network, and also process this online reconstruction and send the data to shore, feed the events, do a rapid reconstruction, and give a response. And also we are sending our own alerts to other partners, mainly through the TATU network. So even though so far no temporal spatial coincidence with neutrino events from the regions of interest have been found, I will give you more details on the contribution to this multi-messenger program. Okay, so concerning the reconstruction performance, so how well can we reconstruct our neutrino events? So for the track channel, we have angular resolutions better than 0.4 degrees for Antares, above 10 TeV, and factor 2 better for ORCA. This is the kind of, this is how a typical track event would look like in ARCA. The main advantage of the muon channel is the excellent angular resolution, also the increased effective volume of the detector, and the drawback is, of course, the larger atmospheric background that we have. Now, for the shower channel, we have about 3 degrees for Antares in angular reconstruction and 2 degrees for ARCA, so it worsens a little bit. But for showers, you have contained events, so better energy resolution and much smaller atmospheric background, so much cleaner events. So one of the main objectives of Antares is, of course, the search for point-like neutrino sources, and both the pointing accuracy and the angular resolution of the detector are important in this context. So an efficient method to infer the pointing performance of a neutrino telescope is to study the cosmic ray shadow given by the moon or by the sun. So you expect basically a deficit in the event density of atmospheric muons that come from the direction of the moon and the shadow and the sun disk. So because of the absorption of these cosmic rays, so analyzing the data in the periods that I indicate here in this slide, we observe this moon and sun shadow with a statistical significance of 2.5 and 3.7 sigma. Also, we are able to compute the angular resolution for downgoing muons with the values that you have here. And these are the contour plots corresponding to different confidence levels. Okay, so as I said, we can cover a very broad physics program studying atmospheric neutrinos, cosmic neutrinos. I will be I will be through some of these analyses in this talk. So first of all, let me tell you about the recent measurement of the atmospheric neutrino flux published recently in this PLB. So we present a combined measurement of the energy spectra and of atmospheric nu-E and nu-Mus in the energy range between 100 GeV and 50 TeV, about 3,000 days of detector lifetime. And then, well, after our selection that includes a BDT selection, you end up with about 1,000 neutrinos in the shower channel and in the track channel. You have here the numbers. And the distribution of the reconstructed events is unfolded in terms of electron and muon neutrino fluxes. And here in this plot, you have the result after the unfolding. So you have the spectra for these two components. And you see, you comparing with measurements from other collaborations, which are in quite good agreement. Okay, so also the measurement of the diffuse flux is very important. This work has been presented already in several conferences in the past. Let me just make a quick update and remind you that after the unblinding of 12 years of data, we observed a small excess with respect to background. Here you have 50 observed, 36 expected in both channels. So even though the excess is not very large, this result leans towards the observation of a cosmic neutrino flux, which is compatible with the one observed by IceCube. And here you have the likelihood profile, and you see the IceCube best fit points are inside the 68 confidence level contour of the analysis. So we try to look for this excess in the tail of the distributions. Okay, so the perspective for ARCA. Well, here of course, one of the main goals of ARCA is also the measurement of the cosmic diffuse flux. And this is the significance as a function of the observation time for 1 and 2 building blocks of the detector. And as you see, well, we expect to reach a significance of 5 sigma in 1 year with 1 building block, so quite fast. Now, let me also review very quickly on the search for point sources. So while atmospheric neutrinos are randomly distributed, neutrinos from point-like sources are expected to accumulate to cluster in this space. So to find these clusters, we follow a maximum likelihood ratio approach, and we have performed 5 different analyses. No coincidence with no evidence for cosmic neutrino sources were found, but let me just flash you the results. So in the first analysis, we scanned the whole sky, we scanned the whole sky with an unbeam analysis to search for spatial clusterings, and here you have the sky map in equatorial coordinates, so with the p-values. So this is the position of the cluster with the highest significance, which is only 1.2 sigma post-trial. We have also surveyed more than 100 astrophysical candidates from catalogs, also investigated the directions of 75 IceCube tracks, high energy starting events, extremely high energy events, and also AMON alerts, and also a subset of 54 IceCube candidates that we investigated in a time-dependent analysis to search for possible transient origin of the IceCube tracks. So in this case, we incorporate to the signal to the background PDFs a time-dependent term in the likelihood. So no significant excess over the expected background was observed for any of the assumed source locations, and here you have the distribution of the showers and tracks together with the directions of the IceCube candidates. Okay. So finally, also we have reported in several conferences the dedicated search that we did on the Texas event. We perform an online prompt search of neutrinos from the direction of the IceCube event. Also a time-dependent and a time-integrated search in the direction of the TXS blazar, and no significant evidence for neutrinos from these directions over the background was found. So we quoted upper limits in the flags that is quoted here. Okay, so the expectations for KM3NeT on point sources are summarized here. So the detector being placed in the northern hemisphere has a good visibility of the galactic plane, so there are very interesting, as I said before, very intense gamma emitters in this region. So here in this plot, I'm showing you some of them for which the visibility is above 50%. And here you have the plot of the estimated discovery potential at 3 sigma level. So the time needed for a 3 sigma detection of the source. So we can reach this level in a reasonable time, as shown here. And on the left, you have the sensitivity defined as the medium upper limit at 90% confidence level for sources with a generic unbroken power law e to the -2 as function of the source declination for comparison with a 7 years of IceCube. You see how the improvement between Antares and ALCA, and also the pushback in the for these sources placed in the southern hemisphere. Okay, let me now move to this interesting, really nice result that has been accepted in for publication. KM3NeT is sensitive to supernova explosions. So this is done from by analyzing the background data from the deployed units that we have now. So it happens that the interaction of neutrinos below 100 MeV produces charged leptons that travel a few centimeters. So even if the light, the Cherenkov light emitted by these electrons individually cannot be reconstructed as individual events, the detection of core collapse supernova neutrinos can be possible relying on the observation of a population of coincidences in excess over the background expectation. So taking into account all DOMs in the detector, you can plot the multiplicity distribution of detected coincidences and exploit this to discriminate the origin in on a statistical basis. So here you have the expected number of events in KM3NeT in 0.5 seconds as function of the multiplicity, and you see the background in markers, and then you have the signal, which is for 3 different models in color bands. So the detection sensitivity as function of the distance to the core collapse supernova is shown here. So our observational horizon for a 5 sigma discovery covers essentially the Milky Way, and for some more optimistic scenarios can extend beyond that point. Okay, also very interesting analysis published this year. This is the likelihood stacking search for astrophysical point-like neutrino sources. So the stacking method allows to assess the significance of an excess of mu neutrinos, introducing, that can induce track-like events in correlation with the location of a list of possible sources. So all the emitters are considered together as a common population. So we have studied different objects, so blazar from the Fermi catalog, radio galaxies, aptic galactic nuclei, also events from IceCube. So none of the tested sources got a significant value, but let me just flash that the blazar MG3 was found to be the most significant among the Fermi sample. And here you have the arrival directions of the Antarctic track events in equatorial coordinates around this most prominent source. We have 5 events around the source, and also at less than 1 degree from the source. And here you have a dedicated analysis that was performed around the hotspot, looking for the time evolution of the emission. So we have the model gamma ray light curve here. You have these vertical lines that indicate the arrival times of the ANTARES events located at an angular distance smaller than 2 degrees. And here you have this vertical line, which is the arrival time of this ice cube track, which is in time coincidence with the placer. So very, very exciting result. Now, let me move to alerts. So more on alerts. So we have been sending alerts to Baikal, and so I just want to call your attention on some, because some of these alerts got positive results. So for 3 alerts, there were multiplets of GVD cascades reconstructed during ±1 day. So now, well, they are Baikal is currently operating with 7 clusters. And for one of these alerts, the one I'm showing you here, up here, we have 2 GVD cascades detected, blue circles here around the ANTARES events in red, and 1 extra track from ANTARES found 9 hours after the alert at a distance of about 2 degrees. So there is no obvious source candidate close to the trigger direction, but we are performing a follow-up with cascade events in ANTARES and with tracks with GVD in the same time window. Okay, so let me move to dark matter searches. Neutrinos are a powerful tool to do indirect searches for dark matter that can gravitationally be trapped and accumulate in the center of massive astrophysical objects like the galactic center. So let me just underline that we have ANTARES only publication and also an ANTARES Ice Cube combined search for dark matter from the galactic center. This is the main result that we published quite recently, where you see here the limit on the thermally average dark matter annihilation cross section when targeting the galactic center with 11 years of ANTARES data, and also the limits. Well, the prospects that we will get with ARCA, which will push the limit back by 1 order of magnitude. Okay, so let me just move to the current status of the detector. So we are currently running with 6 DUs in ORCA and 6 DUs in ARCA. So on the left here, you have the effective area we achieve for upward going muon tracks. So ORCA is in orange, ANTARES in blue, and ARCA in green. So we are already at the level of ANTARES and even above at the highest energies. So another way of comparing the performances is also to look at the event rates. So the number of upward going muon tracks per year with the current configuration. So we get comparable numbers for ANTARES and ARCA. So these are our recent results from the atmospheric muon flux that were published recently. So we have measured the atmospheric muon flux with ORCA and ARCA as a function of depth. So here the trick is to select events with high multiplicity, so above 8 DOMs. So you remove basically all the contribution from natural background, and you get a sample dominated by atmospheric muons. So you can compute the integrated atmospheric muon flux as function of depth, and this is the kind of result you obtain. And you have here also the numbers from ANTARES for comparison. So we are still, of course, tuning the calibrations of the detector and understanding the new lines as they are deployed. But well, with the data we collected right after the deployment of the lines on the time position calibration setup, and also doing Monte Carlos, the results show a good understanding of the detector performances. And of course, the work is ongoing. So the perspective. So this month in June, we expect to deploy 4 more DUs at the Orca site, 3 more after the summer, plus 5 DUs in Arca. So by spring next year, we expect to have 23 Arca lines and 20 Orca lines in operation. So this brings me to the summary, so which is more an outlook, because, well, after the successful operation of Antares, so the main focus is now on increasing the size of KM3NeT. So we are all eager to continue with the KM3NeT science program, because we are convinced that the detector will give very competitive results, and why not maybe some surprises, thanks to its excellent location and also excellent performances. So thanks a lot for your attention.